Hello everyone, and welcome to my channel. We do educational videos on this channel, and we look into different theories of everything in depth and try to shed light on them because they've been suppressed and you probably don't know anything about them. Today is video number 472 that we've done on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson was an engineer in the US in the 20th century. And in 1959, he proposed his two fundamental postulates about how he believed the universe operated. And then through a process of deduction, he arrived at a theoretical universe about what the universe would look like if his postulates were correct. And then he wrote some books comparing his theoretical universe with the empirical, measured, and compiled universe of the legacy scientists. We're looking at one of those books today called Basic Properties of Matter, wherein Larson arrives at equations for many of the basic properties of matter and plugs in all of the elements and compounds and then compares them with the actual results of laboratory experiments and compiled in scientific tables. We're looking at chapter 8 of this book today, or at least we're taking over in chapter 8 of this book. That's called thermal expansion. And we'll get into that before that, we want to at least go into the reciprocal system itself, give you an intro to that, and then we'll look at some of thermal expansion to kind of show you how Larson's thinking goes and how he goes about his study. So the universe of motion is also known, the reciprocal system is also known as the universe of motion, because Larson attempted to build his universe on motion, not matter, not energy, but for Larson, the universe was made out of motion. And in particular, Larson is referring to a kind of motion that he calls scalar motion. This is a motion with a magnitude, but no specific direction. And you can envision a scalar motion if you take a balloon and you put dots on it. If you blow up the balloon, all the dots will be moving away from one another. They will be not moving in any specific direction. Rather, they will be moving in every direction, outward in every direction. Every dot will be moving away from every other dot. And even the locations that are between the dots will be moving away from every other location. So there is no specific direction of that motion. And that motion has been acknowledged by scientists, and even Hubble back in the 1920s had discovered that all of the distant galaxies are moving away from each other. So this motion, now they used that to, extrapolated that to the Big Bang, but that doesn't really make sense, because that would kind of imply that our galaxy is not part of that, and that we are not participating in this motion away from all of the other galaxies. And that kind of goes against kind of the spirit of Copernicus and just the non-geocentric way of looking at the universe. So Larson starts out with scalar motion, and then we'll go into his first postulate, which is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, that's where we get the reciprocal system from. It's from the relationship between space and time, which comprises motion. So motion is the relationship between space and time. Space and time have no independent existence. They only exist together in motion. And motion is basically a fraction, with space or time as the numerator and time or space as the denominator. The most basic kind of motion that we know of is speed. You know, the bike is moving at 12 miles per hour. 12 miles of space in 1 hour of time. Space over time is speed. But all other scientific phenomena are also relationships between space and time, says Larson. They're all kinds of motion. So matter is a kind of motion. Energy is a kind of motion. Electric charge is a kind of motion. Magnetic flux is a kind of motion. Pressure is a kind of motion. And they all have their time over space or space over time signatures. Energy is time over space. Pressure is time over space to the fourth. Acceleration is space over time to the second, and so on and so forth. So this serves as a good system of units, because we got rid of the matter part of the MKS system, the kilograms part, and turned that into time to the third power or space to the third power. And so now we only have 2 variables instead of 3. Now, getting back to that first postulate, space, time, and motion come in 3 dimensions. Space, time, and motion come only in discrete units. Now, when you have that outward motion, which Larson calls the progression of that expanding balloon, the progression, that is, you know, a motion in no specific direction. However, if you decide that you are going to arbitrarily proclaim that one of the dots on that balloon is now motionless, you've assigned a reference point, and you say, this particular dot I'm going to say is motionless. Then you start to create this stationary reference system, as opposed to the moving reference system of the expanding balloon. And by doing so, it appears as if there are force fields between the dots. It appears as if there is a repulsive force between your dot that you've chosen to be motionless and all the other dots that are moving away from it. You've kind of stopped the world. You've created an artificial stationary reference system, and now it appears as if there's a force field between these dots, which there isn't. Larson refers to this as an as-if force. So it looks as if there's a force, but there isn't. And it behaves mathematically as if there's a force, but there isn't. Every dot is pursuing its own course. Every dot is moving away from every other dot. There is no action at a distance, and there is no ether, and there is no force at a distance. Every dot is moving under its own inherent motion. And this gives rise to really the 3-dimensional stationary reference systems. So, one of the obstacles to understanding the reciprocal system has been that for so many thousands of years, we've relied on this container viewpoint, that space and time are the container of the universe, and that, space is this 3-dimensional thing that is still, and that we put on X, Y, Z coordinate space, and that we move through this XYZ coordinate space, and events unfold in time. This time is a scalar motion. Time is always getting later and later and later, but in no specific direction. And so we have what Larson calls the stationary spatial reference system. 3 dimensions of space, coordinate space, and progressing time, clock time. And this is generally the system that legacy scientists use, this stationary reference system. And so this is also a part of the reciprocal system, but it is recognized to be very limited, as 3 dimensions of space are needed just to occupy 1 dimension of motion. You only need 1 dimension of motion to create a 3-dimensional spatial motion. And so that means that if you have 3 dimensions of motion, you're going beyond that spatial reference system. That spatial reference system is insufficient to describe what you need to be talking about with a reciprocal system or a universe of motion. Now, by the reciprocal postulate, with space and time being inverses of one another, you have this same relationship theoretically with time and space inverted. So you have theoretically a place where you have 3 dimensions of time, coordinate time, and you have clock space. Space is still progressing. Space is getting farther and farther and farther apart. But time is stationary and 3-dimensional with x-like, y-like, and z-like coordinates. So that is what Larson calls the temporal reference system. And again, you need just 1 dimension of motion to describe all 3 dimensions of time there. So again, this temporal reference system is also not sufficient to describe Larson's universe of motion. For that, he requires his moving reference system of the progression. And that progression is moving along outward in all directions, at all times, in all places. And it is moving at the speed, at unit speed. Now, Larson says that space, time, and motion all come in discrete units. And so speed, also space over time, comes in discrete units. The progression is moving at unit speed, 1 unit of space per 1 unit of time, in all places and in all time, at all times. This is what Larson calls the empty universe, or the null point, or the universe at rest, the universe of motion at rest. So this is another obstacle to understanding the reciprocal system. You have to be able to conceive of a motion without anything moving. This motion of the progression of the natural reference system doesn't entail anything. It is just motion outward at the speed of light in all directions in 3 dimensions. And that is what Larson refers to as the progression of the natural reference system. So Larson's natural reference system is a moving reference system, progressing 1 unit of space in 1 unit of time. Okay, now that is really the neutral point of the universe for Larson, meaning that half the universe is moving slower than this. Larson calls this unit speed, 1 unit of space per 1 unit of time, is also known as the speed of light. And so the speed of light is the neutral point. Speed of light outward in all directions is the neutral point of the universe. And half the universe is moving slower than the speed of light, and half is moving faster than the speed of light, which goes way against Einstein and generally the scientific community. So you have, Larson refers to these as the material sector and the cosmic sector, respectively. And in the material sector, you have coordinate space and clock time. And in the cosmic sector, you have coordinate time and clock space. So when you cross that boundary, that unit speed boundary, you have to invert the rules and interchange the roles of space and time. Same thing happens within each sector with the unit space boundary in the material sector and the unit time boundary in the cosmic sector. Because remember, space and time are both quantized. There is a minimum unit of space and a minimum unit of time. And if you have two atoms or particles in the material sector that approach each other to 1 unit of space, they can't get any closer because you can't have less than 1 unit of space. So what they do instead is they move further apart in time, which is the equivalent of moving closer together in space. We see it as they're moving closer together in space because we only see time, we only see space, we don't see time, because we are bound to the stationary reference system. We are, by gravity bound to the spatial reference system, and so we only see space, but the actual activity is occurring in time. But we see it in what Larson calls equivalent space. Now, when we see things in equivalent space, we do not see the entire activity. Equivalent space is a two-dimensional region, and it also crosses the time region boundary, and we have to reduce what we see by a certain fraction to account for kind of what is lost in the translation when you are looking across into a different sector or region of the universe. Larson calls that the interregional ratio and equivalent space. And so we've got this time region, and the same thing happens in the cosmic sector, but it's called the space region. When two cosmic atoms or two cosmic particles approach each other to 1 unit of time, they can't get any closer in time, so they move apart in space, which is the equivalent of moving closer in time. And it's seen in time, but it really happens in space. And Larson calls that the space region. And within those regions, you can't see everything that's going on, and also the rules invert. And so now the progression in the time region, the progression is moving inward in equivalent space, and gravitation is moving outward, which is the opposite of what it was in the progression in the material sector and the rest of the material sector, and where the progression is outward and that gravitation is inward. Gravitation is really the, if you take that expanding balloon and now you contract the balloon, the dots on the balloon will all be moving toward each other. That is analogous to gravitation. So that's really where we get matter from. The progression of the natural reference system is the source of everything in this universe. And it is harnessed by taking that outward progression and reversing the motion of that progression and turning it into gravitation. And remember that space-time and motion come in 3 dimensions. So that outward motion has to be reversed in 3 dimensions. It has to be first neutralized, I guess, by what you would call a photon, which is an oscillating motion. It oscillates and appears to be a wave-like motion, really an oscillation on a moving system. But according to Larson, anyway, other of Larson's followers have different ideas about that, we've gotten into before, and we will in the future also. But according to Larson, and then Larson's periodic table is based on three dimensional rotations, rotating that outward motion backwards into gravity. And when you are in the time region is really three dimensions of being in the time region for all three dimensions is what Larson calls the solid state of matter. And in the solid state, when the progression is inward and gravitation is outward, there is a point where they are in equilibrium. Larson refers to that as the interatomic distance. And from there, if you add more heat, it tends to move things apart in the time region. And that would be called thermal expansion. And that's what we're looking at here. And so Larson's equations for thermal expansion, specific heat, compressibility, and so on, all come from those three numbers that he assigns to every atom on his periodic table that are related to the three dimensions that you have to rotate the progression backwards to get the expanding balloon to become a contracting balloon. And so those are ABC numbers. The first number is two-dimensional rotation. The second number is a secondary two-dimensional rotation. And the third number is an optional one-dimensional rotation in the opposite direction. So those are the ABC numbers. And Larson uses those in various theoretical scenarios to arrive at equations for his basic properties of matter. So let's take over and read a little bit here on thermal expansion. I'm sure there's a lot that I didn't cover that Larson will touch on here that I'll try to elaborate or at least explain. And so as a result, we're going to be creeping through this very slowly. But I think it's important to go through just to read it into the record, and also to give you an idea of what Larson is, how Larson goes about this study, and also to recognize that this is a generalized theory. So even though you might not be interested in thermal expansion, what you learn about thermal expansion applies to the rest of the universe also. This is not a pigeonholed theory, just like modern science, where you can learn all kinds of things about molecular this or that, but it doesn't have any application to anything else. This is a unified theory. So what you learn about thermal expansion, you can apply it to things like economics or astronomy or even astrology, or dream interpretation. These things are all covered by the reciprocal system. So you can glean important things from learning about thermal expansion, even by accident. Okay, this is the relative expansion. Now he is talking about, he finally came up with an expression for thermal expansion up to the melting point, which is that place where the time region ends and the atom or molecule escapes from the time region in one of its three dimensions. And at that point, theoretically, the expansion should be equivalent to the interatomic distance, meaning that it should be double. The volume should be double what it was at the interatomic distance. But then he goes through this process of showing how that actual doubleness is reduced by these various fractions, 1/16, because first the thermal motion is an oscillating motion because the progression is canceled. It's an oscillating motion. It's an intermittent motion because the inner motion is canceled. So it goes out and then it doesn't go and then it goes out. So it's only at half speed, but then it's also reduced by 1/8, and then that has to be taken to the 1/3 power. You have to take the cube root of that because it's three-dimensional. And so the number he ends up getting is 0.0205. So theoretically it would be a volume of 2, but that is totally reduced. So now it's a volume of 1.0205. Okay, this is the relative expansion that would take place providing that no change in the volumetric determinants of the substance occurs above the reference temperature, usually room temperature. But such changes occur more often than not, and as has been explained, the volume changes accompanying an increase in temperature are normally in the direction of increased volume. The total expansion is 0.0625 of the initial volume, corresponding to the volume at the solid endpoint, where this theoretical initial volume is greater than the reference volume projected to zero temperature. The expansion expressed relative to the smaller volume is correspondingly increased. It follows that in most cases, the linear expansion, as measured, is somewhat above 0.0205, generally in the range from this value up to about 0.028. I didn't follow that. But again, he's in the weeds here. This is not vitally important if you wanted to understand thermal expansion. But this is, not on the main line that we are looking into for an introductory understanding of the reciprocal system. The increase in volume at the higher temperature where it occurs is generally due to the structural rearrangements. The matter, as it is heated up, undergoes various transitions or structural rearrangements, both of its crystal structure, its geometrical structure, and also its rotational alignment, or what he calls orientation. The changes take place either in the interatomic distance by reason of the transitions from one of the types of orientation discussed in Chapter 1 to another, or in the crystal structure, or both. The expansion is related to the interatomic distance, S sub 0, rather than to the geometrical volume, and it is independent of the geometrical arrangement. Okay, I'm not sure why that is true. I think that's a theoretical statement, and he has an antecedent for it. He probably argued for it at some earlier point, but I do not remember. So the expansion is related to the interatomic distance rather than to the geometrical volume. And it is independent, because it can have a different geometrical volume depending on what its, geometrical crystal structure is. It could be the hexagonal close packing, or it could be the tetrahedral, I don't even remember the names of all the crystal structures, but each one of them has a different volume for the same interatomic distance. So even though the atoms are separated by the same amount. Depending upon the crystal structure that you use, that will create a different volume of the whole arrangement. Okay, and it is independent of the geometrical arrangement, but as indicated in the preceding paragraph, a modification of the geometry does affect the relation of the volume at the solid endpoint to the reference volume at zero temperature. And I'm confused about that. But I think if I took 5 minutes and read it 20 times over, I would probably figure it out. So maybe I'll try to do that off camera, and maybe let you know tomorrow if I can figure that out. But that's kind of how Larson goes. You know, you have to go through it at a snail's pace and try to understand his concepts. But if you don't get them, then you have to move on to the next thing. And you really, in order to learn Larson, you have to learn kind of several different books of his, because he goes into many different subjects: chemistry, astronomy, physics, metaphysics, economics, and uses the same principles in slightly different ways. And so it kind of, sometimes it seems like he's pulling stuff, you know, out of no place, but he's actually being very consistent with how he is applying things. But it seems to be arbitrary if you just look at it kind of one book in a vacuum. So this is not a quick study, and Larson has all the information there, but it is not at the ready for you to grasp it right away. You know, that's why I'm trying to come along, and I hope in the future I can write like a textbook on the reciprocal system, so that I can put the information like at the ready for a good student. It's still not going to be easy, but it could be at least as easy as your high school chemistry class to get the reciprocal system. Maybe in a year of, you know, doing it 5 days a week for an hour, you could have a working fluency of the reciprocal system. As is right now, it takes kind of a heroic effort to get the reciprocal system. And I'd like to leave that possibility open for any heroes that are out there to get it come from my videos as is. But I'd like it to make it easier for people in the future. So hopefully I will be working on that. Okay, we're going to stop there and take over tomorrow.